Hello interwebs, welcome to Let's Fix Computers. I've got a Dell Inspiron 15R, I think it is. Yeah, 15R SE7520 to be exact, that does not power on. I'm just going to go and grab a charger because I forgot to get one before I started recording. This should do. So apparently this has got the old chestnut of the charger cuts out when you plug it in. So let's try plugging it in and seeing what it does. So blue light on the charger, and when I plug it in, the light goes out. So yeah, the charger is cut out, and if I try and plug it back in, nothing happens. In order to get the charger back on, I need to disconnect and reconnect it. So there's the charger tip. Unplug the charger, and then plug it back in again. And now the charger has come back to life again. So this is a short circuit in the laptop somewhere, so it should be a nice easy one. So let's get it apart and see what we can do. I shall take off this back cover. Let's use the P0, I think. Where's my electric boy today? I think it's on the other counter. I might go and get that because we're probably going to have to take all the screws out of this thing. Now we need to take the keyboard out because it's an old style laptop. There we go. Flip that out. So it is a reasonably old laptop this, but it's got an i7 in it. So that's going to be why it's still going strong. We've got more screws on the top then. I think the top cover is going to be coming off of this. So I'll keep it this way round. Right, that one for the trackpad, that's going to be the power button, and this is probably going to be those. And that's going to be our display connector, so that doesn't need to come off quite yet. Right, let's just see if I can pull this apart. Nope, it's going to need some help with the prying tool. There we go, I think that did the job. Something's holding on. What's holding on? Oh, there's another one down there for LEDs, I would imagine. Right. Okay, I'm fairly certain I have done one of these before. Yeah, I thought this looked wretchedly familiar. Thankfully, it's not familiar in the worst possible way. When I saw this laptop, when I took it out of the box, familiarity rushed through my head, and I was like, oh no, it's one of these. I thought it was the same as that one Dell I did way back when, which was blowing up VRM high side MOSFETs. I think it was high side or low side, can't remember which. Blowing up VRM MOSFETs on CPU vCore, and there was all kinds of things wrong with it. I've seen this one before as well. That had a short on the main power rail, and it actually ended up being one of those guys there, which was part of the battery charger, I think. Looks about right. Those are MOSFETs probably going into the battery. So those are probably going to be a suspects for this as well. Right, so let's take some measurements around the power area in the top left of the laptop here. So I'm going to set my multimeter into resistance mode. And firstly, we're going to check for the resistance across the DC jack. So up here, we've got Let's move a little bit across. There we go. So up here we've got 2 reds, 2 blacks, and a white. So that's our positive, our negative or ground, and a sense wire. So I'm going to put my black probe on ground, which is any screw hole. I could also put it on the black wires. Those will also be ground, but screw holes are nice and easy to get to. And so let's see how much resistance we have from ground to DC in. And that is about 130 kilo ohms, so 130,000 ohms, which is lots. So there's no short circuit at the DC jack itself. Most likely the charger is cutting out because the laptop is detecting a fault and telling it to via the sense wire. That's my guess. Although I don't fully know exactly how much communication occurs over these sense wires because it kind of varies. So there's not a huge amount more to see on the top side of the board here. We need, because the positive pins, they go into this trace here and then they go through the board. So we kind of need to see the other side of the board to see where they're going after that. They're probably coming out somewhere else in the laptop, maybe over here. Although I think this is the battery charger circuit, but it doesn't matter. The point is, ideally we want to trace them all the way. So we want to get the board out and see what's on the other side. We do have a current sense resistor here though. So this guy here, PR102, that is a current sense resistor because it's a big fat surface mount resistor, which I can't quite make out. I think I can actually. Can I scrape some? No, I can't see what the value on that is. However, it's a big fat resistor and it's got 2 little wires coming out from the middle that are going down to this chip here. And those 2 wires there, those are the sense lines. So this is a very, very low resistance resistor. And it is causing a very, very slight drop in the voltage going across it. And this chip is sensing that tiny voltage drop, which allows it to calculate how much power is, or how much current is flowing through the chip. So this is probably the main current sense resistor that allows the laptop to detect how much power it's consuming, and so on and so forth. So let's see what the resistance is over there. And we've got more or less a dead short circuit. We've got 0.6 ohms. And that will go even lower if I press down even harder. So like allowing for probing and stuff like that, that's basically 0 to all intent and purpose. So there is definitely a short circuit. There's a short circuit at this current sense resistor, which, as I say, I'm fairly certain is the main current sense resistor in this. So we've got a short on B+, the main power rail, which is where it often is, to be honest. And that's good because that tends to be one of the more fixable ones. The other thing we can observe as well is that because that is 0, it's not 1 or 3 or anything like that. That's a dead short circuit, which probably means there is a shorted capacitor or some kind of major failed component. If we saw that there was like 1 ohm or 3 ohms or something like that, that might be a short via the PCH or the CPU or the GPU or something like that. However, because we've got absolute more or less 0 there, I'm fairly confident that we're going to have a bad capacitor. So what we're going to do is take the board out, do a visual inspection on it, and I think we're probably going to go straight to voltage injection here. Out we come. There we go. So now we're on the other side of the board, we can see a little bit more about what's happening. So this is where our main power comes in. On the other side of the board, as a reminder, we've got the positive rail comes in, it goes to this pad here, and then there are vias, that's VIA, vias, so multiple of them, which go through the board, and they come out here. So they come out onto this pad, then they go through this inductor or a coil, and that inductor is there just to smooth out transients and inrush. So when you plug the charger in and suddenly all of the wires energize, and suddenly all that, you know, it's like connecting a when you connect your garden hose up to the tap and you open the tap, the hose suddenly goes whoosh, as all of the water rushes into it. That's inrush or transient, where there's suddenly a surge of movement as empty wire suddenly fills up with electricity, as it were. So this guy smooths that out. It just slows it down ever so slightly just to stop there being a shock of power going in at very high currents. So that smooths out transients and stuff like that. So it comes in here, and then it gets to the inrush limiter, which is, I mean, the name inrush limiter, I don't know how many people actually call it that, but this is what it's called on a MacBook schematic. So that's why I call it an inrush limiter. But at any rate, it's this pair of MOSFETs here. So what we do is we go into the first one, then we go into the second one, and then we go out onto the main power rail. And these two create a digital switch, which is controlled by the power management chip, which is going to be this guy here. And this guy can switch off those MOSFETs to kill power into the laptop, which is exactly what is happening here. This guy is detecting the short circuit with its current sensing resistor, and it is switching off those MOSFETs and sending a turn-off signal to the charger. Hence why we have these exact symptoms. So again, if we follow the traces, we go through these guys, we go out of here, and again, you'll notice that the pads stop there. And under this, we'll find more vias which come out there. And then they immediately go through that current sense resistor to here. And once again, there's another group of vias. And it comes up here. And then we now have our main path into the laptop. So that is our main input rail into the laptop, which is sometimes known as B+, VIN, BAT, or whatever, you know. I think most schematics seem to refer to it as B+, which is kind of misleading because B+ would be battery plus. But then if you're running off battery, then the main power rail is technically B+. So I will sometimes use those terms interchangeably, whether it's B+ or VIN or the main power rail. From context, you see what I'm talking about. So what we can do now is we can double check where our short circuit begins. My prediction is that it will begin here, and we'll find that all of this back here is absolutely fine. So let's just confirm that. I'm going to put my multimeter into beat mode. And remember, there is a time and a place for beat mode. So at the moment, we're in resistance mode, so it just tells me the resistance across the probes. So 0 because they're touching, plus losses. Wow, look at that. There's actually quite a lot of loss. I need to get some fancy probes because I've got 0.5 ohm just in my wires here. Anyway, now if I go into beep mode, then it just beeps when they touch. And it will give me a reading as well, but it's not as accurate. So the time when I use different modes, firstly, if you have a fancy multimeter, it can probably do both at the same time. But I like to use cheap multimeters because A, fancy multimeters are very expensive, and B, cheap ones are just fine for general diagnostics. And I like to use cheap tools where I can to show people that you don't necessarily have to have super expensive stuff. This AN8008 is like, I don't know, 20, 30 pounds, which is quite expensive for what it is. But again, it's very accessible. It's got a nice big screen on it, despite being a small unit. And yeah, it's a quick multimeter. I'll stick an Amazon affiliate link for this down below. It is the one that I use in my general repairs. So that's my shilling session over. Moving on. So in beep mode, what we can do now is we can just check these. So there's our short circuit. We are also shorted back here. So that will be as well because it's connected. But we're not shorted there. Alright, so this guy is open. Or rather, it's closed. We're shorted across there, which I wasn't expecting. So now I'm going to do a inspection of the board, or further inspection. I'm going to take off the heat sinks and stuff, and I'm just going to see if I can spot any failed components. Now, I'm hilariously bad at this, so I'm not expecting to actually see anything, but I will continue to try because that's how you get better. So let's just take all the covers off, and then we'll see if we can spot anything that is cracked or darkened or discolored or something like that. Okay, there's basically nothing under this black plastic. Nothing of note anyway. So let's start doing an inspection. So now the places I'm looking for is stuff that will be powered by that main power rail. So I'm looking for any secondary power supplies. So a secondary power supply is where that B plus rail, that main power rail, is being converted to something else. And the giveaway is generally you'll see more MOSFETs. So the MOSFETs on this laptop are reasonably old and they come in two flavors. We've got these style of MOSFETs, which again is what the inrush limiter was built up with. And then for the more power intensive stuff, we've got these flat ones like here and here. So where we find groups of MOSFETs and inductors like this, and once again if we go up here we've got MOSFETs and an inductor, that is a secondary power supply that is powering something. So near these secondary power supplies we're going to see, we've got the MOSFETs, and we're typically going to see surface mount capacitors like these guys nearby. It's probably one of these guys that's gone bang, because it always is. So we want to inspect those, and again I'm looking for ones that are cracked or have visible issues. I'm going to go in for the super close-up for this. So that group of 4, those seem fine. I'm hoping we might spot something just so you can actually see what we're looking for when it happens. So those look all right as well. Let's go down to this group area over here. That's obviously power to something, maybe. That all looks okay to me. Fine. Let's see, we've got the back of CPU V core. Those guys look happy. Nice creamy browns. All right, what about the top of V core? That all looks okay. All right, what about GPU V core? Okay, GPU V core we've already looked at. It was this section right up at the edge of the board. So we've got a high side MOSFET there, and on the other side of the board we've got the inductors and the low sides. So there's no additional capacitors up here worthy of note. So yeah, nothing to see there. Got a cluster there. Those guys look a little bit grey, but discoloration is not really indicative. What I'm looking for is something that actually looks like it's fractured. See, like that guy there in the middle of the screen, that almost looks like it's fractured, but that's just a hair, I think. Yeah, it's a hair. However, in that moment, that looks like it had a crack across it. That's what we're looking for. I'm not seeing anything. So I'm going to go straight to voltage injection, because voltage injection will immediately tell us what the problem is. So let's prep for that. See, here's the thing, is I could just go straight into this and do all of this at top speed, and we could have this thing fixed up in 10 minutes from the start, and it would look very good and I would look very clever. But it's very difficult to actually learn when someone goes a mile a minute and it's just suddenly blink and they're like, it's that one, and you're like, okay. So I'm trying to go slowly and methodically, so you know, for the people who are looking at this, figuring it out, learning it, they can see what I'm doing and get the confidence to have a look themselves. I'm by no means the best at this by a long shot. However, what I'm trying to do is make this accessible. And if I can make this accessible, so I can make it so people feel like they understand the video and that they're willing to give it a go themselves, that's op success. Right, let's take out anything that we can take out. So I'll take out this RAM as well. What is that? That's 8 gigs of DDR3 low power. Socketed CPU, thank you very much. Let's get some jumper wires. These will do. Will they do? Have I got something a bit beefier than that? I have. There's some nice big beefy jumper wires that I've used before. Cool. Right, so you guys have seen this before. See if you can tell what I'm going to do next. We're going to put a ground wire on a ground point. So I'm going to pick a screw hole. Where's my soldering iron? Warming up the soldering iron. We're going to put our black wire on a screw hole, and I'm going to put my red wire. We can put the red wire anywhere where the short circuit exists. My usual choice for this is the current sense resistor, because it's a nice big part that is shorted on both sides, and you can literally just blob your wire on top of it, and it won't mind. It's an easy thing. You won't break it. You're not going to snap it off the board. So it's a very good place to solder into. It's also sort of replicating being as close to the charger as possible as well. So let's tin up these pads. Wire's trapped. Stick a blob of solder down there. And put you on. And we'll stick a blob of solder there. And we'll put you on. So now I have two wires that have a short circuit between them, like so. There we go, there's our short circuit. And what I shall do is I will connect those up to my bench power supply, and I will pass 3 amps at 1 volt into these wires. And what that will do is, firstly, it is bypassing all of the circuit protection that is switching off the charger. So the laptop will be unable to do anything about this power. It cannot switch it off. Therefore, the power will flow into the shorted component, wherever it is on the board, through the shorted component into ground, and come back out the black wire again. And that shorted component will start heating up under that 3 amps of current, because there's very little stuff on this board that can tank 3 or 4 amps without burning out. So we're going to pass the current into the device, and then we're going to figure out what is getting hot. And I will figure out what is getting hot by using a thermal camera. Now, if you don't have a thermal camera, you can use the touchy-feely method, where you just simply run your fingers across the board on capacitors and stuff like that until you find the hot spot, which is how I used to do it. I've got videos demonstrating that method. And it's reliable. It's reasonably reliable, but slow is the downside. You can. There is also the alcohol method, because if you spray alcohol onto the board, then it will boil away where the hot spot is. But I found that to be very unreliable, because a lot of the time there's not enough heat to really see it in a meaningful manner, in my experience. It does sometimes work, but I don't think it's reliable personally. It's good for confirming. If you think you've got, a bunch of capacitors right next to each other and you're not sure which of the 3 it is, you could spray some alcohol on there and the culprit will suddenly go bone dry. So that's a time when it's very useful. And then finally, the other common method is known as the Rosen flux method, or Rosin, the flux method. And what that is you burn some flux to create a load of flux fumes, and you waft them over, and it deposits a powder coating of flux across the top of the board. And then when you apply the power, the hot spot will suddenly go and a little puff of smoke and leave a hole where your short circuit is. That is a nifty trick which I have seen video demonstrations of but haven't tried myself. I think it's quite a messy method, if I'm honest. However, it seems to be very reliable. And power on. Okay, we've gone down to 2.6 amps at 1 volt. So we haven't got a great connection into our short circuit here. There's enough resistance that the voltage has built up to 1 volt. In an absolute dead short, we should see the voltage being lower than that, because remember, in a short circuit, effectively these 2 wires are touching, so the potential difference between them is 0. But we've got 2.6 amps going into that. Let's see if that's enough to see anything. you probably wouldn't see anything with the touchy-feely method here. Hey, there it is. So it looks like it's the MOSFETs. However, be wary of calibration. The calibration on this is slightly out. If you look at the ghosting effect around that screw hole, don't know if that's coming out in the video, the overlay of the thermal image versus the visible outline is out of alignment. So that hotspot is actually over these capacitors here. So let's go in and show those up. So firstly, with my finger, ow, yes, that's burning. So yeah, my finger is burning hot. There's not a lot of residual heat in that area, so that would have been difficult to find with the touchy-feely method if I didn't know exactly where to put my finger out. Now let's get the alcohol. And if I spray some alcohol in there, you can just see the second one up is bubbling away under the heat there. It's very difficult to see. Let's give it the beans just for the lols, because we found our guy and we know we're not going to damage anything. We're going to get anything else out of it now. I'm torturing this just for science. That makes the alcohol method very apparent now, because it's viciously boiling the alcohol. Look at that. Bubbling away. So if we gave that some time and possibly 5 amps, we'd probably see that capacitor actually crack and fracture. But I'm not going to go any further because I'm not going to risk damaging the board. Because the problem with the touchy-feely method and the alcohol method is you need more heat to be able to actually find the heat source. And if you're putting in more heat and more power, you're risking damage to something else in the board. Because we don't want the next weakest component to then immediately fall over as well. So let's turn that down again, and then let's turn it off. So let's go back down to there. Right, I'll turn on my hot air station at 450 degrees maximum airflow, and we're just going to blast this guy off the board. So the resistance across our probably dead capacitor is 0. Oh, I've fallen off of it. There we go. So there's our shorted capacitor. And so we now should find that there is no longer a short circuit on the motherboard. So I'll measure between ground and the current sense resistor, because that's where we were testing from. So black probe on ground, and the current sense resistor is now at 2 mega ohms, or 1.8. It's stuff is energizing. The point is, it's not shorted to ground anymore. Lots and lots of ohms. So our fault is repaired. So I guess now the only thing that remains is, shall we replace this capacitor? And I shall, because I can. So I could. So now we need to figure out what value this capacitor was before it short-circuited. So we could take a guess at it. I could remove this one next to it, which is exactly the same size, and we'll probably find that it's the same value. However, what I will do, because I have a collection of schematics, I'm going to see if I have a schematic for this board that can tell me. Because if I have a schematic, it means I don't have to guess, which is why schematics are important and why manufacturers should make available schematics so people can fix their stuff. So this is an LA8241P. Let's see if I have one. Hurrah! I do have one. Okay, so here is the schematic for this laptop. So the area that we were removing the thing from was up here, and this was next to PQ108 and PQ110. So let's search for PQ108. Here we go. So what is this page? This is power charger. So this is the battery charger, which is, I think, what I originally predicted, although I'm not sure if that actually made it into the edit or not. But at any rate, so this is the battery charger. So here is that charge control chip. So that's the one I was talking about. And if we have a look up in the top left here, you can see here is our DC in, which is labeled as V in. Then it goes through those two MOSFETs and then into the current sense resistor, PR102. This is where we were injecting our power from. And after that, it becomes B+. So that kind of supports all of the stuff that we've been talking about. And likewise, you can see we've got those two sense wires going down to this chip. So this chip can detect how much power is coming through from the charger. Likewise, if we go over to the right here to where the problem is, these two MOSFETs are creating a buck regulator which can charge the battery. So that goes over to BAT+. And after we've had the two MOSFETs and our coil or inductor, it goes through another current sense resistor. And that current sense resistor, again, it's got two sense wires that go back to the chip as well. So it's got sense wires to detect how much power is coming in from the charger, and it's got sense wires to detect how much power is going into the battery. And if we go a bit further up here, we've got another MOSFET here, and this is for power coming out of the battery and into the laptop. So there's that. So interestingly, I don't think there is a current sense for power coming out of the battery. We've got current sense for power going in, but not out. So make of that what you will. Anyway, so we need to figure out where that capacitor was. So was the capacitor labeled on the board? It was not. However, it bridges between PL101 and ground, because PL101, that's the output inductor, and the other side of the capacitor has to go to ground because these are power capacitors. So what we'll find is that this is the high side MOSFET and this is the low side MOSFET. So switching over to the schematic, we've got the high side, which is PQ108, and the low side, which is PQ110. So notice that the low side goes down to ground and the high side goes up to the power source. I've explained before how buck regulators work, but the short answer is this chip will switch on these MOSFETs in pulses. So it will switch on a pulse of this, so we get a pulse of 19 volts coming through here. Then it energizes this inductor with that pulse of power, so the inductor charges up. Then this switches off and the chip pulses this MOSFET, which bridges this side down to ground, which creates a negative terminal here, a positive terminal here, and then we have power output from the coil. So by only allowing in just a little bit of 19 volts at a time and charging that coil just a little bit but rapidly, we managed to step down the 19 volts down to whatever battery voltage it is. And that's how a buck regulator works in a very short sense. So the capacitors, those are bridging PL101, which is up here. There's PL101 to ground. So it's going to be one of these guys because it was directly on PL101 and ground. So what have we got here? We've got 4.7 U, so U is going to be micro, 4.7 microfarads, 0805, 4.7 microfarads, 0805. Then we've got a 0.1 microfarads, that's 100 nanofarads. And then there is a 2200p, so that's a 2.2 nanofarad. So, and that correlates with what we can see on the board. We've got two big boys, a medium boy, and a tiny little boy. So if I actually turn the board round, so that's actually in alignment with what we see on the schematic, we've got two big ones, a medium one, and a little one. So there is a range of capacitances there to filter out a range of different frequencies that we want to filter out from that line. The important thing is the two larger ones are the same value. They're both 4.7 microfarad. So I'm going to dig into my collection of capacitors and get a 4.7 microfarad. Right, so we are looking for 475, which is 4, 7, and 5 zeros. 470. That 478 or 475? 478, that would be like 470 microfarads, and you'd never get 470 microfarads into a tiny little thing like this. You need big boy caps for that. That's what all these guys are. So like this one here with 330 written on it, that's 330 microfarads. It's got to be this big, huge, honking electrolytic. So I'm pretty certain that's supposed to be a 5. We can test it. I'll put my multimeter into capacitance mode. So I've gone up to resistance, and now if I press my mode button a couple of times, we get farads in the top right. Or in this case, it starts off at nanofarads. And I'll just hold the probes over there for a moment. There we go. 4.08 microfarads. So that's a little on the low side. We were looking for 4.7. However, capacitors have a very wide tolerance range, like 20%, and these are cheap capacitors. However, they don't need to be very good. As long as you're in like the correct order of magnitude, it's going to work just fine. So that guy will be absolutely okay. Let's stick it on the board. See that smudge there that's just appeared? That's from the flux fumes, from the flux that was in the solder. This is what the rosin flux method does. You deliberately burn a load of flux, so it leaves this residue all over the board, and that just wipes off. So yeah. Okay, where's my new capacitor? It's that one. I'm going to put a blob of flux in there. I could probably have soldering iron heroed this, but you'll get a nicer and straighter finish with a hot air gun. I'll just squidge you in there. All right, and time for hot air. I'm going to turn my airflow down a bit. Still going 450 degrees, but I've turned down to 4 out of 10 on the airflow, just so I don't blow everything away. There we go. Right, now I'm going to drown everything in alcohol just to get rid of the flux residue that I've left on the board. There's my toothbrush. So ironically, we probably could have done all of this from the top. Probably could have taken some guesses. And that's the thing, is if you want to do this fast and economically, then you want to get to the point where you're able to just immediately take stabs in the dark that will probably get a result. And you might even be able to do this in 10 minutes flat without ever taking the board out of the laptop. But obviously these videos are here for people to learn from. And unfortunately, that means we've got to do things the long way. But you know what they always say is show you're working. Right. These are all top covers. That's going on. at this point, it would be prudent for me to plug in the charger before I go to the trouble of putting everything back together. So what I will do, I'm just going to stick on the top cover, because if I put this on and plug these wires in, then we can actually turn the laptop on and make sure we get a post screen. So let's do that. So there's no hard drive in there at the moment, so it's not going to actually boot up, but we should get a picture on the screen. So charger plugged in, and the charger light has stayed on. Power button. The fan is spinning. It's beeping. Okay. It should be able to run without the keyboard attached, so that's probably a memory error. What I will do, I'm going to click this down because that's enough for me to be confident that we're there, and then I'll just reseat the memory. However, this top case is not sitting properly. I think I've got the DC cable in the wrong place. I just took out the memory modules and swapped them over and put them back in again. So that wasn't very scientific, but it was a case of I have reseated them and I've swapped them around just so they're definitely reseated and they're not gone back into the same place again. So let's try that again. It's power cycling. Okay, that's memory training, I would imagine. There we go. It's booting. How? Did this thing have a sneaky little SSD in it that I didn't spot? It was probably on the motherboard. I don't care. It was probably on the motherboard somewhere. I am bamboozled, but it does not matter. Let's carry on reassembling. I have won. I win. It works. That's the wrong screw. I need the smaller ones. Okay, and now with the charger plugged in, we have a battery charge light there, and if I press the power button, we get hard drive LED and a bit of a dim but an on power LED. As you can see, the power LED is on, it's just kind of dim, and the laptop is booting. That's all I've got for you today, so thank you everyone for tuning in. I hope you guys found that interesting and or informative. As always, my support links are down in the description below for Discord, Patreon, Twitter, Instagram, stuff like that. And as always, if you liked the video, hit the like up, the thumb up button, because that tells YouTube that people want to watch this video. And I'll see you next time. Bye! Okay, time for... thumbnail. That's the one. Thumbnail. Okay. Let's see. Let's turn it off. And then I've got to hold it up to the camera. Move that out the way. And we've got to smile just as the Dell logo appears. Here we go. Is it on? It appeared. All right. Bye.